Hey, welcome back. Today we're going to be talking about how to solve rotational kinetic energy problems with combination shapes or systems of particles for AP Physics C Mechanics as well as AP Physics 1 or just general physics classes. Alright, so let's go ahead and get to it. First of all, I've got about the simplest problem you can create to talk about the different styles of addressing the problem that you can do. You can either address this as an individual points combined sort of method in thinking about translational motion. That means moving from point A to point B in terms of kinetic energy. We've been doing translational motion since the beginning of the year, and then rotational motion is different, and we can think of that as a system and solve the problem that way. Either way you solve the problem is valid. It just kind of depends on what you have to work with, and you can convert from one form into another. So let's go ahead and get to it. This problem says let's imagine a system of 3-point objects or 3 masses attached to massless rods as they rotate. Each sphere has a mass m, lengths of the radii are given as r, and the system is rotating with an angular velocity of omega, or you could say the point masses are moving with the speed of v. What is the rotational kinetic energy for the system? So like I said, there are two different ways of thinking about this problem and addressing the problem. You can think of this as having a speed. It's really a tangential velocity, but we'll call it a speed for now because we're dealing with energy. And so we don't have to worry about the direction so much. That's why energy is easier than dealing with vectors like kinematics. In any case, we can think of this as individual points combined. And what do we know about that with kinetic energy? We know that is equal to 1/2 mv squared. So we can take the kinetic energy of each of the 3 points, put them together, and I'm going to contrast that later. I'm going to show you how to do this as a system using rotational values. Since we do want to compare the two and see how they turn out, we can immediately start to think in terms of this equation right here. This equation is what I've called small but mighty because you can take this, and this is the translational version of variables and so on that we're dealing with, and this is a rotational version of variables. So you can actually use this small but mighty equation to interchange between either translational or like linear variables versus rotational variables. So we can just sub this in and see what happens if we want to compare the two different scenarios here. So we can then say kinetic energy is 1/2. We'll call this capital M because the problem gives this to us as capital M. And notice we can sub in r omega for these v values. So I'm going to do that, and that is v squared. So we'll call this r squared omega squared as we apply the squared function within the v there. And that is for 1 point mass, right? Well, 1 point mass, well there are 3 point masses, right? So we could take this whole thing and just say, let's multiply it by 3 because there are 3 point masses. And so you would end up with 3/2 m r squared omega squared is equal to k. Alright, now let's treat this as a system. So another way to approach the problem is instead of treating them as individual points and thinking them as using translational motion, let's think of them as a rotating system and see what happens there. We do have the rotation version of kinetic energy, so we can go ahead and write that, and what we need to think to ourselves is what is this I value? Since they're point masses, that's going to be mr squared, but because there are 3 of them, we're going to say 3 mr squared, and we can't forget omega squared at the end, and if we just multiply these together, you can see that if you do the problem this way, you end up with 3/2 mr squared omega squared. Now check this out. They are exactly the same in the sense that you'll get the same answer however you do the problem, however you want to approach the problem, or whatever you're given with the problem. You can do it in either way. And so that's an important idea here with about as simple of a problem as you could approach, but demonstrating a really important concept here for how to approach problems with rotational kinetic energy. In any case, I've done lessons on an entire year of physics and almost an entire year of AP Physics C Mechanics. If you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.